Well, it's really wonderful to be back at Davis, as always. This is I guess, a slightly unusual talk. I think it's a very important subject. I think I have a unfortunately well-earned reputation for not ending talks on time, and I think Yara figured out how to solve this problem. So the colloquium is scheduled for 2 hours in order to shame me to ending in 1. No, but more seriously, I would like to say at least my own thoughts about this important question, and the idea for the length, don't worry, the talk is not going to go for 2 hours. We might even stop at the hour mark and clap, and the people who don't really care that much about the future of particle physics can go. But actually, you can do that now. I won't be offended. You can just go now. But I really thought that after at least my own remarks about it, those of you who are interested, you can have a discussion about it. So I think so. This is an important time to be thinking about this question. I think the more apt title for this colloquium, which it's a title that is a question that's in the minds of probably many of you, whether you admit it or not, is that, okay? Okay, so is there a future for particle physics? And this is something that is said loudly or softly, depending on where you are. Everyone knows the refrain by this point. We had the LHC made a spectacular discovery of the Higgs particle. We haven't seen anything else. Certainly 3 or 4 decades of theoretical speculation about what might be seen next has not borne fruit. And it's not at all obvious where the next threshold is for producing new particles. Before we turned on the LHC, we knew there was a physical phenomenon involving the weak interactions that just implied a breakdown of physics unless we had some new particles beneath a scale of around 1.2, 1.3, something like that, TeV, 1,300 times the mass of the proton. And the Higgs was it. The Higgs was the one extra degree of freedom that was needed to solve that problem. I'll quickly review it. So we knew ahead of time that something was going on. We knew since Fermi something was going on at the Fermi scale. We knew more specifically that something was needed before discovering the Higgs or something like it. So in that sense, there was a guarantee of some threshold of new phenomenon to be probed by the LHC. But now that we've found the Higgs, we've have this complete theoretical structure that can, in principle, be self-consistently extrapolated to much, much higher energies than the energies that we can conceivably probe on planet Earth. And so there are lots of theoretical arguments. We have to see a lot of stuff other than the Higgs at the LHC. None of those arguments have seemed to be true, at least so far. And I should emphasize, this is not remotely saying the LHC is done, we stick a fork in it, etc. Right? The LHC is going to gather about a factor of 100 more data than it's gathered so far. There's a huge amount still left to do and analyze. But something that you should know, if you're not a particle physicist, is that there's a reason why we go to higher energies as much as we can, rather than just gathering more and more data. Obviously, if you want to have access to particles at a given mass, you need enough energy to make them. So that's the most obvious thing. Something that's a little bit less widely known outside particle physics is that the rate for producing particles at a fixed mass scales something like the 5th power of the energy of the machine. So a factor of 2 in energy is buying you a huge amount. So every leap of even a factor of 2 or 3 to make an energy is a humongous deal compared to then just gathering more and more and more data. So it's still entirely possible the LHC will discover new particles beyond the Higgs. There's a very exciting experimental program that's going to keep going for another 10 or 20 years. But I would say from a theorist point of view, if you turn into a pumpkin at midnight, it's 11:45. Okay, that's the situation that we're in, and that's why it's reasonable to wonder what would happen if we don't see anything beyond the Higgs. Now, This is something, as I said, some people talk about loudly, some people talk about in sort of hushed tones, worriedly. And I think it's just that there's nothing to be worried about, there's nothing to be scared about, it's just something that should be talked about very openly, right? And it's just a fact about nature, it's a surprising fact about nature if it's the way things turn out to be. But let's assume, for the sake of this discussion then, that we're not going to see anything other than the Higgs particle. So we don't know ahead of time what the next threshold for a discovery is. And then you'll notice a certain cognitive dissonance in this subject, depending on who you talk to. If you talk to people like me, I have said in public lectures, I say to my colleagues, I say to all sorts of people, this is a stunning time to be a physicist. The questions that we have to struggle with are huge, enormous ones. It's tremendously exciting. If I could ask my parents to change when they would conceive me so I could enter science at a different date, I would ask to be a graduate student now, right? So I say that and I believe it, okay? I believe it to my core. On the other hand, there are other people who say, oh gosh, you know, it's all over. How can we convince anyone to build another machine? We don't see anything other than the Higgs. Politicians will never build something else for us. And it's all like boo-hoo and sad and depressed and worried. How can both these things be true at the same time, right? Somebody is full of it, okay? So, or someone is wrong, or more likely they have different attitudes and perspectives on what's important. So what I'd like to do in this talk is explain. Explain my own attitude about it, and explain the origin of this cognitive dissonance. Of course, I think the answer to this question is an absolute resounding yes, but I would like to talk about what I think the future is. So, one way of framing what the problem is the following. I think there's a fraction of people who think this is the definition of particle physics. Particle physics is something like the study of the ultimate building blocks of matter. And that may be something that attracts some people to the subject. I can tell you personally, this actually, if anything, delayed my entering particle physics. I was actually repelled by this aspect of it, okay? Because after all, this feels a lot like chemistry. And I nearly flunked chemistry many times in my life, okay? So it feels like the chemistry of the 20th or the 21st century. And who gives a crap, you know? So you go, you have this particle, you give them funny names, you make 7 of these, 4 of the other kind. Whatever, right? You know, some people care, but I can tell you this is not why I care about particle physics. And that's not really what particle physics is, at least not merely that. To me, what it really is something much more basic. It's a study of the fundamental laws of nature that are governed by, in many ways, still mysterious union of the principles of space-time and quantum mechanics. And if that sounds a little grandiose, even the notion of what a particle is fundamentally is tied to the symmetries of space and time. For example, the reason we say the word the electron for an electron that's here as well as an electron that's there and there is that the universe is approximately translationally invariant. So its properties are the same under translations. The reason we call an electron moving in the x-axis the same as the one moving in the z-axis because of rotations. Is because of rotational invariance. If we didn't have space-time symmetries, the notion of a particle would not be a useful one. So to begin with, particle physics is deeply tied to the symmetries of space and time, Lorentz invariance and translations. The very notion of particle is deeply tied to that. The main reason we've been studying the interactions of particles at shorter and shorter distances, higher and higher energies, is that we've seen over the past 100 years that a lot of the essential simplicity and unity and deep principles governing the laws of physics are obscured by what we see as kind of long-distance accidents, but become manifest when we study physics at very, very high energies. But it's the laws that we care about. The particles are like the alphabet. The laws are the novel. We're interested in the novel. And that's at least the main reason I've been attracted to the subject and continue to be attracted to the subject. And so, depending on your attitude to the answer to that question, then you have a different answer to this question, right? So everyone is interested in seeing new physics. So does new physics mean that we have to see new particles, right? And as I just said, if you think this, if you think that for something new and exciting to happen, we have to see new particles, and if you also think we need a guarantee for the energy scale at which new particles will show up, then we can just stop having this discussion. Okay, then we should stop, because unless we do see something at the LHC, but for the purposes of the discussion here, I'm assuming that we're not. Unless we do, just as simply the flat-out truth, we do not know where the next particles will show up. So if this is the line in the sand, then it should just stop. Okay? And if you need that guarantee, of course, right? You could have the attitude that you just go to the frontier and see what's there. Fantastic attitude. But if you need this guarantee, we do not have this guarantee. However, this is way too limited a view of what new physics is, at least in my view. What we really care about are new phenomenon, really new phenomenon, that are associated with new principles. That's what it's really about. And I think, I'll come back to this in a moment, I think part of the attitude that what really matters is new particles is a generational memory of the people who are not just my generation, my advisor's generation, of thinking back to what is largely considered to be the sort of golden period of this field in the 1960s, which really was about a particle every other week and this explosion and the whole zoo and the rapid progress and all of that stuff. And it's true that back then things moved incredibly rapidly. But I would say that they moved incredibly, and this is not to be to diminish the incredible accomplishment of the invention of the standard model of particle physics. But if you come back in 200 or 300 years, that will not be the crowning glory of the 20th century. You know, the big deal of the 20th century was the discovery of relativity and quantum mechanics. Those were the things that were really revolutionary. And then there was a lot of work after that to figure out which precise relativistic quantum theory describes nature. That was a very important work. But the reason the progress was so fast is because the scale of things that had to be accomplished was not as high as what was needed in the revolutionary period in going from the classical world to the relativistic quantum mechanical one. And it's not just me saying it. You know, I know personally many of the discoverers, the theorists anyway, who were involved in the discovery of the standard model of particle physics, and they say this themselves, that the magnitude and scale of the questions that we're struggling now are just a completely qualitatively different character, and deeper and more profound, as I'll try to explain, than the ones that had to be struggled with then. And in fact, it's anomalous in the history of fundamental physics. The typical timescale for progress has been always measured in decades and sometimes centuries, and not on the timescale of weeks, months, and years. And furthermore, some of the most important experimental discoveries don't involve plots with giant spikes in them, okay? Which is what the 60s were about. You know, probably the most important experiment of a little over 100 years ago was the null result of the Michelson-Morley experiment, right? This is not seeing something. A simple null result had probably a much greater and profound influence on the way we think about physics than many other positive results. So what I'd like to say is that it happened to be that, new particles can tell you about new physics, but it's certainly not the only way of learning about new physics. In fact, the most profound new physics that we discovered in the last century was not associated with experiments of that sort, the ones that told us about the really revolutionary advances of relativity and quantum mechanics. What we care about are new phenomenon and new principles. And where we are today with the discovery of the Higgs, nothing else, exactly the period that we're in, has opened up a set of questions and forced us to confront a set of questions that I personally believe are just as profound and difficult as the questions that people struggled with in the 20s and 30s in the transition from the classical to the quantum mechanical world. So I think the questions that are on the table are really deep, profound structural ones. We definitely need input from experiment to tell us how to go, especially because we have not covered ourselves with glory as theorists in making correct predictions about what accelerators would see. And so that's what I want to spend the rest of this, at least first part of this lecture talking about, is why I think we're in such sort of a bifurcatory, important juncture in the history and development of the subject, why it's more crucial than ever to continue the experimental exploration of a really, truly new phenomenon, the existence of an elementary spin zero particle like the Higgs, something like which we've never seen before, and what the options are on the table for doing something about it. All right, but just to put the importance of the discovery of the Higgs in some context, let me give a very quick review of kind of theoretically what we learned in the 20th century. I think you could summarize, to me, the most important lessons of the 20th century after these two big revolutionary discoveries of relativity and quantum mechanics, that these two principles together are so incredibly rigid that they largely dictate what the universe can possibly look like at very long distances. So this is a colloquium all in itself, I think a very nice colloquium all in itself, but if you just hand these laws to competent enough theoretical physicists and lock them up in a room and tell them to come up with universes that are compatible with these two big principles, they would, if they were good enough, they would come back with this amazing answer. They would say, if at zeroth order I ignored the masses of the particles, I imagine that all the particles are massless, which should be a good approximation as I go to really high energy collisions where I can ignore mass. Energy dominates everything. So if I begin with the approximation that all particles are massless, you have to tell them that there is such a thing as flat space. Big, huge, flat space. You tell them that. You tell them about translations and Lorentz invariance and quantum mechanics and the existence of a big, huge, flat space and say, go. Then they would deduce the existence of particles. They would understand that it's a good idea to ignore mass in the first approximation, and then they would see whether it's possible to combine these principles together, and they would find that it's incredibly hard. Okay? And they would come back and tell you whatever is going on at long enough distances, it's guaranteed that I'll have elementary particles that can have an interaction where the interactions are dominated by the simplest possible one, where three elementary particles meet at a point in space-time. That's all really interesting. You could have had more complicated fundamental interactions, where 4, 5, 7 of them meet at a point in space-time. But at long enough distances, it's guaranteed that only these ones are going to be the ones that really matter, and concatenated together give all the more complicated phenomenon that we see. And that furthermore, the particles, the massless particles, they have a very tiny menu of spins. They can have spin 0, 1/2, 1, 3/2, and 2. And they'll tell you funny things about them. They'll tell you this massless spin 2 guy, there can only be one of them. You can't have 7 of them. It can only be one of them. It has to have a peculiar property that has universal strength interaction with everything. And if you happen to have massive things around, it makes them go around in orbits. So it's gravity. There's no falling elevators. There's no Einstein thought experiments. They don't need to look at the world to deduce the existence of general relativity. It is a consequence of special relativity and quantum mechanics as one of the possible ways the world can be. The spin 1 particles have to have very special kinds of interactions. Anyway, so you can have at most 8 of these spin 3/2 guys. They tell you all sorts of interesting things about this spectrum. And then we're in now if you let them look at the world, we're in the interesting situation where you see the universe make use of some of these things. The spin 2 guy is the graviton. We've seen fundamental particles of spin 1/2, spin 1 certainly, photons, gluons, W and Z particles at very high energies where you can treat them as massless and so on. Okay, and before July 4th, 2012, this was the menu that we had seen nature make use of. So we're in the interesting situation that the universe was making use of a subset of all the possible things it could use compatible with its grand principles. Okay? So as I said, this is a colloquium all in itself. It's a fascinating story how we know that this is true, and I think it should be better known. But now something very important happened. There was only one little bit of there was one footnote to that story, which was that all of that is true in the approximation where you treat the particles as massless. And you might think that's trivially a good approximation when you go to really high energies. But there is one very important case when particles have spin where having a little bit of mass is a discontinuous thing. You can't be a little bit massive just like you can't be a little bit pregnant. That's because massive particles with spin have extra spin degrees of freedom compared to massless ones. And it's a famous simple fact. You know that photons has 2 circular polarizations. So 2 helicities is a quantum mechanical photon. But a massive spin 1 particle must have 3 spin degrees of freedom, because you can always go to a frame where it's at rest and rotate your head to see it spinning in all 3 possible ways. So there's this discontinuous difference. 2 is not equal to 3 between massless spin 1 and massive spin 1. And that means something. That means that if you want to go to very high, if you have a collection of massive particles at low energies, and you want to imagine what they look like at very high energies, all the degrees of freedom they have to reassemble into these legal allowed ones for massless particles at very, very high energies. And it's not guaranteed that that's going to happen given the spectrum of particles that you have at low energies. That's why we knew there was something missing in the picture of the world before the Higgs particle was discovered. By some simple counting on your fingers, you could figure out that the degrees of freedom that were associated with the particles of the weak interactions, there just weren't enough of them to reassemble into these legal ones that were allowed by these grand principles at very high energies. And we had to have an extra degree of freedom. Now, this indicates one of the sort of classic problems that we have in fundamental physics for theorists. You have some experimental problem, or in this case even an internal theoretical one, but you can't just make anything up. We're very, very constrained. After all, there's this tiny menu of possibilities that we can turn to solve any of our problems. And in this case, you could go back and say, could there be anything here that we have not used that we could use to solve this problem? And the answer was yes. All you needed was a single particle, one single particle of spin 0, to be that extra degree of freedom that was needed for the physics of massive particles at very low energies to smoothly interpolate to massless particles at very high energies. That's the deep content of the story of the Higgs and the Higgs mechanism. You'll notice nowhere here have I drawn pictures of Mexican hats and waxed poetic about symmetry breaking and all of that. That's one particular language for talking about what the Higgs is about. It's a perfectly correct language. I suspect if you come back in 100 years, that language will be used much, much less than it's been used over the last 20 or 30, because it's very dependent on a particular language for describing the physics rather than something about the physics itself. What I explained to you is exactly something about the physics itself, and is the most invariant and correct description of what the story of the Higgs is about. The story of the Higgs allows us, for the first time in our history in this subject, up to July 4th, 2012, everything we had, the theory we had was always breaking down around the corner just from internal theoretical consistency. Finally, we have something that can be extrapolated to exponentially higher energies. Then we can have difficulties involving quantum mechanics and gravity and all that stuff near the Planck scale. But there's no internal theoretical difficulty, no clash with obvious principles that stops us from this extrapolation. So it's interesting. The story of the Higgs now turns that the red 0, which indicated we hadn't seen an elementary particle of spin 0 before, into black. That's what's exciting about the Higgs. It's not just hype. The Higgs is not like the top quark or like the bottom quark or the tau meson or the tau particle or any of the other things that were seen before. Very important, very exciting they were there, but they're not qualitatively different from the things that we'd seen before. The Higgs is qualitatively new. We've never seen something like it before. We've never seen an elementary particle of spin 0. And I'd now like to explain a couple of the reasons why having such, so on the one hand, this is the mystery of the Higgs. On the one hand, it's the simplest elementary particle you could imagine. It has no properties at all other than mass. It doesn't have spin, it doesn't have charge, it just has mass, nothing else. On the other hand, that very simplicity is associated with some deep theoretical mysteries. So there are two ways there's various ways of describing this mystery. One of the important things about a particle of spin 0 is that it's possible in another language to talk about the following thing. Namely, if a particle has spin 0, you could imagine some collection of them that have really tiny momentum. Imagine incredibly tiny momentum. So quantum mechanically, that means really long wavelength. And you might take a limit where the momentum is so tiny, it's like basically the wave function is spread out and flat over the entire universe. Okay? So having particles of spin 0 allows you to imagine these condensates exist without violating any symmetries of the world, like Lorentz invariance. So you can't do that with particles with spin because it would pick out a direction or do something else that we know is not there. But particles of spin 0, this is possible. And that means that the physics of the Higgs and that of the vacuum are much more closely connected to each other than for any of the other elementary particles. Okay? So, for instance, there's this famous estimate for the energy density of the vacuum. If you just add up the half h bar omegas for bosons and fermions for the universe in a box, you get this famous, enormous, huge energy density that scales like some high energy short distance cutoff to the 4th power that would lead you to suspect that there's enormous vacuum energy that should, by all rights, have curled up the universe to have a minuscule curvature. This is the famous cosmological constant problem. But because the masses of the elementary particles are related to this condensate value of the Higgs, the subleading part of the calculation here also has a piece of the energy density of the vacuum that now depends on what the size of this condensate of the Higgs is. That should also, by the same logic, give you an enormous amount of inertia or mass for the Higgs. So this little back-of-the-envelope calculation has two big puzzles of physics in it, the cosmological constant problem and the hierarchy problem. And these are technical ways of talking about it. A less technical way of talking about it is we don't understand the answer to a very simple question. Why is there a big macroscopic universe? Okay? That's probably the most obvious feature about the universe, is that it's big, even though it's governed by microscopic laws that hold sway on very short distances. And why is that? Why is the universe big? Especially when there are violent quantum mechanical fluctuations that are increasingly violent as you go to shorter and shorter distances. How is that short distance violence compatible with this very smooth, clear, long range order that we see on scales of 10 billion light years? So we don't have a good answer to this question. Why is there a macroscopic universe? And there's another way of talking about this problem that highlights more the importance of the fact that the Higgs is an elementary particle of spin 0. So imagine the following question. So one aspect of why we have a macroscopic universe, first, the universe is big, and we don't know why the universe itself is big. That's the cosmological constant problem. If the energy in the vacuum was as big as it should be, the universe should have been curled up to a minuscule size. But secondly, the universe, which is big, has big things in it, like planets and you and me and so on. We are big even though we're made out of small atoms. Why is that? That's a direct reflection of the weakness of gravity. It's a nice exercise for undergraduates to calculate, in terms of fundamental parameters, the size of the Earth divided by the size of an atom. Okay, the Earth has the size it has because the gravitational pressure that wants to crush the Earth is balanced by the atomic pressures holding it up. So it's a back-of-the-envelope estimate that you can do, and you discover that the ratio of the size of the Earth to the size of an atom is exactly the square root of the ratio of the forces, the electric force to the gravitational force between a pair of protons. Okay? So that ratio is the ratio of the fine structure constant divided by g Newton times 2 proton masses. That ratio is 10 to the 36. Its square root is 10 to the 18. And indeed, the Earth is around 10 to the 18 times bigger than an atom. Right? But the universe is big, therefore, the Earth is big precisely to the extent that gravity is weak. And if you imagine cranking up the masses of the elementary particles, and everything will get squashed down to little microscopic black holes, and no large structures would exist, even if you had a big universe to begin with. So the question of why there's macroscopic things in a macroscopic universe boils down to the question of why the masses of the elementary particles are so much smaller than this Planckian mass, where gravity would be strong compared to would be as strong as everything else. And so you can begin with a question like, why is the photon massless? So that's gone to an extreme. It has zero mass. It doesn't go all the way up to the Planck scale. It has zero mass. And you have to apologize, it's a somewhat crappy cartoon. I don't like this analogy, I don't like this metaphor so much, but people sometimes talk about, you know, the quantum mechanical vacuum as having some structure like particles and antiparticles popping in and out of existence all the time. You might wonder, why is it, and when the photon propagates kind of through this medium, why doesn't it pick up a big inertia as it does so? And there's a deep answer to this question. And the deep answer is that it's because 2 is not equal to 3. Okay? See, any interactions, if in any approximation you manage to get something that looks like a massless spin 1 particle, then this is guaranteed to be stable under any little perturbations you do around it. And that's because the number of spin degrees of freedom changes discontinuously between massless and massive. So you can't go from having 2 degrees of freedom to gradually having 3. Okay? The force of this argument also explains why our friends in condensed matter physics have an easy time, not trivial, but they can engineer condensed matter systems, beautiful condensed matter systems that at long distances are described by effective quantum field theories that have many of the same building blocks that we've seen in the standard model of particle physics. They have things like emergent gauge fields, so they can get things that roughly look like an emergent photons, or even chiral fermions, and so on. So many of the basic building blocks of the standard model, you can even engineer in the lab. Why can you engineer them? Because once you find roughly the sort of right material that does it, its existence is stable and robust for this reason, for this 2 is not equal to 3 reason. Okay? The one thing our friends in condensed matter physics can't easily do is make something like the Higgs. The Higgs is the thing which is unusual. The Higgs is what makes the universe not look like a piece of metal. Okay? Otherwise, qualitatively, the study of, you know, to me, if we had seen much more complicated dynamics associated with the Higgs, which many people would have been thrilled to see, strong interactions, you know, things like analogous to things we've seen in superconductivity or in QCD, that would be great. But to me, and I'm just speaking for myself, to me that would be a strong sign to stop studying this part of the physics, because it's the same kind of phenomenon that we engineer all the time in the lab in condensed matter physics anyway. And then you can do more fun things with it and do, you know, play all kinds of other field theoretic games and do all sorts of other cool stuff. But it's not the universe. It's not the relativistic vacuum of our universe. And our universe is special. The relativity is special. It's not just a garden variety condensed, like a garden variety condensed matter system. And the Higgs is the clue. It's the main clue that it is not like it. Together with the existence of gravity and other things, which of course involve much deeper challenges to our notion of to many other notions. But I mean, at accessible energies, things that we're probing experimentally, it's the Higgs, which is the sign from nature telling us, I am not a random metal. I'm not like a metal. I'm something different. Okay? So I think that's why it's very, very important. And sorry, I forgot to say, why is this a problem? Because it's not true for the Higgs. The Higgs is spin 0. There is no difference between the number of degrees of freedom of a massive spin 0 particle and a massless one. 1 is equal to 1. So there's absolutely no reason we should expect a particle like the Higgs to not have a mass that's as heavy as it could be from these arguments. And the fact that we've seen the Higgs and not a whole bunch of other things that gives us an explanation of this phenomenon is the thing that many of us are very confused about. All right, but in summary for this part of the discussion, I would say that the Higgs is really new physics. In a literal sense, we've never seen anything like it before. We've never seen something that looks like an elementary particle of spin 0. The fact that it's there, nonetheless, without any of the other bells and whistles that theorists have expected for 4 decades, should A, teach theorists a bit of humility, but B, it's clearly a harbinger of some profound new principles that are at work in the quantum vacuum. Now that's a lesson for theorists. I have to say that it's not clear what theorists are doing with this lesson right now. I think a lot of us are still sort of reeling from the news. I'm exaggerating a little because some minority of us are not surprised by this at all. And it's not a tiny minority. I belong to the minority that's actually not very particularly surprised by these developments, but that's a separate story. I'd say the majority of the theoretical community is very surprised by this. But in any case, that's for the internal belly aching of theorists. If you're an experimentalist, it's totally obvious what to do. You've seen this new thing. You've never seen anything like it before. You have to just study it and look at it closely. And what does that mean, look at it closely? This brings me to the main subject of the talk. So I want to talk about what I think of as the clearly most important next step experimentally in particle physics, which is to think about, seriously think about, and begin trying to get the next generation of colliders after the LHC. So I want to talk about motivations for great big circular colliders. The things that people are talking about are around 100 kilometers around. And they could operate in, you could use them to do two things. You could use them to collide electrons. Sorry, this is so hard to read. You could use it to collide electrons and positrons and produce millions of Higgs particles as the Higgs factory and study the properties of the Higgs in detail. And you could also use it to collide protons up to around 100 TeV energies, around 7 times higher than the energy of the LHC, and go to the energy frontier. And what I want to do in the rest of the talk is argue why this is what we need to do to study the Higgs. So very importantly, what I'm going to try to, what I want to argue is that this is what we need to do, even if we don't know where the next threshold of new particles is, even if there's no guarantee that we're going to see new particles when we go up there. I'm not saying we should do this because around the corner is everyone's favorite supersymmetric theory or extra dimensions or this, that, the other. Those are arguments that, in my view, were incorrectly used to motivate what we would see at the LHC, or even machines that have been talking about like for a long time, like the linear collider. Always the best argument for studying these things had to do with the theoretical mysteries we knew we had involving the Higgs. Those theoretical mysteries have just deepened with the discovery of the Higgs and nothing else. And so that's what I want to talk about. Why it is that to shed light on this question and tell us which of two bifurcatory roads we have to go down or more, we need to have these great big circular colliders. Okay? So let me go back to the questions about the Higgs. So as I said, what's important about it is we've never seen a point-like spin-zero particle before. We've never seen a point-like scalar. So question number one is, how point-like is it? That's an obvious experimental question. So how do you decide what we mean by a point-like? You decide, how do you decide if you have a complicated collection of charge from very, very far away, all you see is the monopole, right? But if you're trying to detect whether it's actually made out of if the collection of charge is more complicated, you could do two things. You could go up close and look at it, if you can do that. So that's the analog of building a higher energy accelerator and just going there to see. Or you could see from further away whether you can measure dipole moments, quadrupole moments, right? So these are smaller effects that can tell you about substructure there is. So the way to look at something and see if it's point-like is by looking at it. And the most obvious way of looking at it is to bounce light off of it. Okay? So you want to bounce light off the Higgs. Okay? So that's the most obvious sense of looking. Now, the Higgs is a pretty unstable particle, so it's hard to keep one sitting there and bounce light off of it. But fortunately, one of the things that it does is decay to a pair of light particles, photons. Okay? So for instance, studying the pattern of decays of the Higgs to two photons, which is one of the classic modes in which it was even discovered, tells you something about whether it's point-like, whether that's compatible with a point-like structure or substructure. But more generally, you can take the Higgs and see how it interacts with other particles. Okay, so this is one of the most important couplings. See how a Higgs interacts with two Z particles. And now, what we know today from the LHC, and what we'll probably know through to the end of the running of the LHC, is not going to be too different than this, is really something roughly like this. So when we say something is point-like, what we really mean is we don't know if it's an infinitesimal mathematical point. We mean that it looks like it has no substructure on a scale comparable to its Compton wavelength. Okay, so that's true of the electron, for example. The electron Compton wavelength is 10 to the minus 11 centimeters, and all the interactions of the electron that we've measured down to 10 to the minus 17 centimeters are compatible with a point-like structure. So it might be a little loop of string at 10 to the minus 30 centimeters, but that doesn't change the fact that over a huge range of energies it looks effectively point-like. Contrast with the proton. right around the scale of its Compton wavelength, you see that it's a big, messy bag of stuff, quarks and gluons and all sorts of other things. And this is basically the picture we're going to have with the Higgs. Indeed, from the LHC, we're seeing that it looks point-like, more point-like than its Compton wavelength, but not by that much. You know, maybe we'll know that it's more point-like by a factor of 4 or 5 compared to its Compton wavelength. And indeed, with LHC resolution, that degree of point-likeness would be almost exactly the same as the degree of point-likeness that we've already seen in the early past of in the relatively early past of particle physics. When we go down to the scale of nuclear physics, the pion is a spin-0 particle. The pion looks a little bit elementary over a range of distances that's roughly 3, 4, 5 times smaller than its Compton wavelength. Okay, so the mass of the pion is around 130 MeV. So here's its Compton wavelength, the inverse of that, and the length scale where you see sort of new substructure associated with the pion is, for example, associated with the rho meson is around is around 1/770 MeV. So that's what we'll know about the Higgs, roughly speaking. Okay? In other words, we could be done with the LHC, and we would not know whether the Higgs is really super point-like or is more or less as point-like as the pion. And I hope I don't need to convince you that those are two sort of radically different pictures of what you're led to two radically different pictures of the world, depending on which one of those things you believe. After all, the pion is in the end composite made out of other stuff. And so then the fact that it's a spin-0 particle is not the end of the world and was not associated with a revolution in our understanding of the quantum vacuum and all that stuff. It had a boring explanation, perfectly interesting in detail, but foundationally boring explanation. So that's where we'll be. We study everything about the Higgs at the LHC. We will not know convincingly, whether it's more point-like than a pion was or not. And if there are specialists in the audience, we could argue about factors of √2 here or there and how to scale things and so on. But this is definitely qualitatively correct. So it's not, more than this, that's something David Gross likes to emphasize. If you want to understand phenomenon at a scale E, you don't go to energy E, you go to 10E, because you don't want to be in this sort of stupid transition period where it's not obvious what's going on. That was true, certainly true for QCD. The energy scale of QCD is a few hundred MeV, and if we stopped probing QCD at a few hundred MeV, we'd be in the muck for a long time. You want to go to a factor 10 higher, just so you really, zoom out big enough to see what's actually going on, and you're not arguing with your friends about factors of √2 or 2 here or there forever. Okay? So that's what we're going to know. We might know the Higgs looks kind of point-like, but it might still be something like a pion, right? That's a very unsatisfactory state of affairs. So here is an invariant question, a really invariant question. Is it like 10 times more point-like than the pion? Okay? That's a reasonable question. I think, do we get an order of magnitude on, can we probe that with an order of magnitude more power? And that's what a Higgs factory will do. Okay? You can make millions of Higgs particles, and those millions of Higgs particles will really take it to a picture that looks like that. In fact, for literally this coupling that involves the coupling of the Higgses to a pair of Z's, which is the most important from many points of view for probing the substructure, because the Higgs has so much to do with the physics of the weak interactions ultimately. We'll improve literally that coupling relative to the LHC by almost a factor of 30. If we make millions of Higgs particles and study them at a Higgs factory. And then there are many, many, many other couplings that are improved across the board by factors of 5 or 10. But for this one, it's something like a factor of 30. And importantly, here we'll know for sure if the Higgs is like a pion or not. Okay? So we'll at least cross a threshold of other things that we've seen before experimentally, and we'll just either we'll see something that has substructure, half of the 80% of people will be thrilled, whatever, or we won't. But one way or another, we have an invariant answer to a question. Okay. Okay. So that's one thing, and that's what the E plus E minus Higgs factory will do. That's its real purpose in life. Now, there's one final thing that you want to do if you want to see whether the Higgs looks point-like, is you want to see not only whether the Higgs looks point-like to external probes like photons and Z particles, but whether the Higgs looks point-like to itself, whether it interacts with itself in a way that's compatible with being point-like. And here there's really something, I think, fascinating. The Higgs is the, as I've emphasized many times, it's the simplest possible elementary particle. That's its mystery, right? Its very simplicity, the fact there's only one spin degree of freedom, no charge, nothing else, that's exactly what makes its existence so mysterious. So that's the funny thing about the Higgs. It's so simple, but the simplicity is what we don't understand. The simplicity has some other things that go along with it. And one of them is this. The Higgs is the only elementary particle we know that can interact with itself. Having three Higgses come together at a point in space-time. That's the simplest possible interaction you could have in the world, and we've never seen it. Only the Higgs can do it. Okay? I can see the specialists in the audience saying, wait, everything does. Don't gluons interact with each other? The W's and Z's interact with each other? Every other thing which interacts has a quantum number that changes. It's never the same elementary particle with itself. Either charge changes or spin changes. Even the graviton, which has a nonlinear self-interaction that's responsible for the bending of light and other things like that, has a polarization that changes. It has a helicity that changes in its three-particle coupling. Okay? In fact, the graviton is the only other elementary particle that could have an interaction of three of them with itself, but that would involve a correction to general relativity of such a minuscule amount that it would be, completely unobservable in any conceivable experiment. Okay, so this is the only other elementary particle other than the graviton that enjoys the privilege of being able to interact with itself. We've never seen this interaction. The LHC won't even tell us it's there. Okay? I mean, people claim that they might see it at the sort of 50% level, but we're not talking about even definitively knowing whether it's there or not. You want to know if it's there, and you want to know if it's compatible with looking point-like. And for that, you need to produce billions of Higgs particles, not just millions of them. You need to produce billions of Higgs particles. And that's something that a 100 TeV collider will do. So a 100 TeV collider, this is something it'll definitely do, make billions of Higgs particles and see this self-interaction, even measure it to around the 5% level. Okay, so you want to know what are the things we'll learn. So we can't promise you that we will see new elementary particles. Okay, we don't know where the next energy scale is for that. On the other hand, what we have gained instead is this dramatic problem involving the simplest possible elementary particles, giving all sorts of large-scale challenges to understanding of the relativistic quantum mechanical vacuum of the world. And the study of that particle, putting it under a microscope by these two machines, will give us definitive answers to, is it as point-like as a pion or 10 times more point-like? A, and B, does it look point-like to itself? And can we see the simplest possible interaction between elementary particles in nature associated with it? Those are things that we will for a fact learn from these experiments. Now we could have a discussion in the second part of the talk. Is it good enough? Is it exciting? Is it bad? But I don't care about that part. I'm telling you the truth. Okay, so this is what we'll learn, and now we can decide whether we think it's important enough or not to pursue. My own view is that there are some fraction of people in particle physics who find these questions really compelling. I think it's an order 1 fraction, both of theorists and of experimentalists, who find these questions compelling, and an order 1 fraction who don't. And I think the order 1 fraction who don't should just do something else with their lives. And the order 1 fractions that do should work on it. And I think that's it's a very basic, there's a huge number of things to do. But there are a number of people who think this is worth spending 20 or 30 years of their life doing. I certainly agree with them. And I think and once you agree that you think there's something worth spending 20 or 30 years of your life doing, that's when you talk about going to politicians and this and that and the other. Those are like fourth order issues, right? The idea that politicians are sitting there being, oh gosh, I don't know, I thought the MSSM was going to be discovered, but no, it looks like you're wrong. And it's so ridiculous, right? It's so ludicrous that they're so knowledgeable, especially now in this country, for fuck's sake, right? But even putting that aside, it's so ridiculous that they have this sophisticated level of knowledge. It's the scientists who have to tell them why what we're doing is worth it or not. And we have to decide for ourselves why we think it's worth it or not. And I suspect a lot of the people who make these arguments about politicians are people who really, for themselves, don't think it's worth continuing if this is the state of affairs, and that's fine. And that's fine. That's perfectly fine. I'm not making a value judgment about it. There's a big world out there, a big intellectual world out there. And if there's only 5% of people in the field who thought this was worth spending 30 years of their life doing, then we should stop. But it's not 5%. I mean, you know, I think by now we know it's an order one fraction of people, and I certainly think it's worth pursuing. Anyway, this is the full stop on the scientific, what will be scientifically accomplished by this experimental program, and then there are many other things that we could talk about. So, There are now all sorts of other things. Here's one more totally obvious one before we do some more examples. I mean, the most zeroth order reason to do these experiments is you know, our, as corny as it might be to say, is our centuries-long human desire to go to the frontier and see what's there. If that's not convincing enough, then everything else is, I think, if you need to be convinced by something much more detailed than that, I think that's, that has to be the leading reason you want to do something like this. So 100 TeV collider especially blasts into the high energy frontier, and it'll have access to particles roughly 10 times higher than the reach of the LHC. And because these vacuum quantum fluctuations that affect the Higgs scale quadratically with energy, that factor of 10 there is giving us roughly a factor of 100 power relative to the LHC for the probe of these quantum mechanical fluctuations. So it's a big deal to gain that factor of 10. Okay, so I can stop there. So you see we're kind of a third of the way through the transparencies. Yeah, maybe I can stop there and see if there are any questions or desire for discussion about this so far. So just to say that the rest of what we could talk about are more detailed, I think very important questions, other questions other than just looking at the Higgs, but other very important scientific questions that we'll get a clear answer to from these machines. So I was going to spend a few transparencies just telling you something about both the Higgs factory machine and the 100 TeV collider, you know, roughly what they're capable of doing, the precision that the Higgs factory will reach, the kind of reach for new particles and new phenomenon that we'll get from the 100 TeV collider, and then talk about three sets of important theoretical questions where the amount of precision we gain from the Higgs factory and the amount of energy we gain from the 100 TeV collider are enough to robustly settle some questions. Okay, there's no real no-go theorems in this business, but really, I mean, you could say, why do you need only a factor of 30 improvement in the precision of Higgs couplings? Why not a factor of 1,000? Or why do you need a factor of 10 more energy? Why not a factor of 500? Okay, and it depends on the questions you're interested in. But there are some very important questions where the factor of 10 to 100 on precision and the factor of 10 in energy will really robustly give us answers. And the questions have to do with the nature of the electroweak phase transition. They have to do with the physics of WIMP dark matter, and finally this sort of hoary and complicated theoretical notion of naturalness. So those are three things I think we'll get definitive answers to. So anyway, that was the plan for the rest of this discussion. But maybe we can. Yes. Yes.
So maybe you just started getting to this, but you started the talk talking about how you're very excited about this point in time part of the course. Wish you were a grad student now. Let's just imagine a horrific, or maybe not horrific, future where 100 TeV collider sees no hint of new phenomena. What would do you think there would still be room beyond that?
We're talking about like 40 or 50 years from now.
Yeah.
Well, I mean, I can't extrapolate forward in time to think about what the experimental opportunities might be 40 or 50 years from now. Do I think, and you know, that's something I will say. I think one of the really good things about all of this is that it helps sharpen and clarify your thinking for why you're doing what you're doing. I think it should be understood that if you're going to work in fundamental physics, this is a highly risky subject. If you're a young person, this is a very risky subject. If you want some certainty in what's going to happen with your career, your life, so don't do it, right? Do not do it. It is a subject meant for people who are risk takers. It has been for centuries, for millennia, okay? And it will be for centuries and millennia, and don't let anyone tell you otherwise. No one promised you a rose garden. The number of people who have spent their entire lives, never mind, generations of activity barking up completely wrong trees that went nowhere is very large. That's the nature of the beast. So you have to decide. I think you have to know that going in. What's the upside? The upside is that you get to struggle with this problem of eternal significance. That's the upside. So you have to decide, if it's worth it or not. Those of us who do it think it's worth it. But I would say that we cannot, as theorists, we cannot be left in this limbo. It's really a limbo right now. I've thought about these questions my entire career, okay? And I'm not getting a clear answer from the LHC. I'd like to say, well, everything that people thought for 40 years was crap. But it's not so strong a problem to be totally convinced of that. It's not, we're not talking about factor of 20 problems. We're talking about factor of 2, 3 problems compared to even, reasonable theoretical expectations of the last 20 or 30 years. Are these ideas that have been so successful for the last 100 years that led us to expect things like supersymmetry or strong dynamics or other things associated with the Higgs, are they just flat out wrong, or are they a little wrong? Is there a wrinkle on them? We just don't know from the LHC. And I, for myself, can't imagine a world where we just decide to stop working and thinking about these problems, because I walk around in this big macroscopic world around me, and it bugs me that I have no idea why the universe is big, even though we can do all sorts of other fancy schmancy things, right? So it's we're theoretically in a totally unsettled place, and it's not about some detailed random question. It's about a kind of a basic feature about the union of relativity, quantum mechanics, and the vacuum, as I said. So I think you're asking, let's say we settle the question. We build a 100 TeV collider, we settle the question, we say up to that energy there's still nothing, it looks just like the standard model. Then I think we have a much, much clearer answer to that question. It's true we have the answer to that question 40 years from now, 30 years from now, okay? Okay, well that's the business about the rose garden, right? Sometimes important questions take centuries to solve. That's why what matters sociologically is simply that there are people like Kepler thought it was worth, or Tycho Brahe thought it was worth spending decades of his life staring at the stars, only to have Kepler figure out what it all meant. You have to have people who are willing to do that. But if you have people who are willing to do that, there's no technological reason to stop going. There's no economic reason to stop going. It's nothing has changed in the historical development of where humanity is, how much these things cost compared to what they've cost before. Nothing. They're more expensive than they were before. The world is richer than it was before. The ratio is basically fixed. There's absolutely nothing which has changed. You look back and say, this was the time in history we decided to stop for no reason. There is not any invariant reason to stop doing it. Purely from, just even purely from any pragmatic perspective. And when you add that to the fact that it's at a time when we're theoretically more confused about these important questions than we've ever been before, I think it's just absurd to stop.
Motivation. I was just wondering more about what other avenues would there be.
Oh yeah, well no, there are many other avenues. I'm personally very excited about work I'm not doing myself, but I'm very excited that a lot of theorists are spending time thinking about cool, exciting ways to use atomic physics, quantum coherence, etc., to look for very, very weakly interacting particles like axions and dark matter and so on. That kind of tabletop experiment for fundamental physics is a wonderful avenue, and I think it's great, and the people who are doing it are doing fantastic work. In my view, it can never be the heart of the subject, though, because you're looking for weakly interacting things that are out there. They're not so directly tied to the deep conceptual questions of the subject that are being raised by what I just told you about.
So like you're saying, no matter what we will learn some very fundamental things about the Higgs. no matter what.
Exactly. Yeah. No matter what else. That's why I drew this line. I mean, you know, many other things could happen, and then you could have many other motivations. But I want to say, you close everything else. Just the mysteries associated with the Higgs, to me, is a totally solid case for both of these machines. Okay. And now it's a question of whether there are people who are willing to build it. I mean, part of the reason I've personally been very excited about the prospect that China might do it is that you know, despite all kinds of other complicated feelings that you might have about particle physics being under the thumb of an authoritarian regime, though, you know, so much for us to speak right now. But anyway. Is that it's one of the very few things I can think of where, you know, I like to say when there are things that you want to do for idealistic reasons that someone else wants to do for Machiavellian reasons, and they're the same thing, that's good. You should just do it, right? And I think this is a case where I think China has indicated that they want to lead a major international scientific project. They're, you know, very high up from the central government. They've said that a number of times. And you tick off all of those boxes, there's not many things that could be. To lead a major international scientific project, the cost is not an issue in China. It's been repeatedly stressed to people there. By the way, it's not an issue here either. But we have our heads stuck so far up our asses that we have other problems. So that's it's not a problem here either. This business about these colliders being not that expensive, they've been uniformly 1 part in 10,000 of GDP going back to the 1970s, okay? And it's hardly changed since. So these things are not, they're more expensive than they were 30 years ago, but that's because everything is more expensive than it was 30 years ago. As a ratio has not changed particularly much. And so the cost isn't the issue there. And I think it is probably the unique thing they could do that would guarantee that they would lead the world. And they spend some money, and then they're the world leader in some important part of science. So that's their internal reason for doing it. I think it would be wonderful for science. It would be to engage 1 billion more people actively in fundamental physics. We probably need a big injection of not just funding, but talent, everything to run something like this. That'll involve tens of thousands of people. And so I'm enthusiastic about it for that reason. And I think it's not, I mean, it's far from obvious that they'll do it, but it's serious. It's a serious possibility that they will do it. So it's not totally pie in the sky. It's something that could conceivably happen.
Yeah, I had actually a
Yes.
simple question about your technical point really. Why is the point Higgs so important, and what would change if it turns out to have some composite structure?
Well, you know, the proton has some composite structure. And the compositeness of the proton means that this analogous question of why the proton is so much lighter than the Planck scale has a very good answer. In the, it's something I explain a little in the actual rest of the slides, but I can explain here that really the issue is when you have when you have a particle with some mass m, the real question is where is the theory revealed that allows you to calculate its mass? Okay, so in the standard model, the mass of the Higgs is a parameter, so we have to take it from experiment. Okay. You might think that there's a deeper theory which actually allows you to calculate it with fewer parameters, or at least different parameters. Okay, so the question is, where should that physics reveal itself? At what scale should the physics responsible for telling us that the Higgs is lying around at 125 GeV? Where should that reveal itself? In every other case we've ever seen this in nature, when you have a particle with reasonable strength interactions, as the Higgs has, with a certain mass, the dynamics involved with being able to compute its mass, the theory that explains where it comes from, is never revealed at an energy scale that's much higher than its mass. Okay? So in the case of the proton, there's hardly any mystery at all, because you get to the scale of its mass, you see that it's not even remotely elementary. It's made out of all these constituents, and those constituents are, you know, they're free when you go to very high energies, and so there's totally different physics that explains where that scale comes from. But there's no, but there's compositeness associated with the proton, and that just trivially explains the, and similarly things were true with the pion. So in the case of the pion, I told you the pion kind of looks point-like, well, let me give you a more ancient example. Here's an even more ancient example. Is the electron itself, right? So we have the electron looked point-like. If you look at the classical self-energy of the electron, it's divergent. And people like Lorentz and Abraham in the early part of the 20th century tried to build theories where the electron was a little shell. And that leads you to a prediction for how big that shell should be, so the classical self-energy of the electron isn't much bigger than mc squared. That's the classical radius of the electron. That's around 10 to the minus 13 centimeters. And even though their model was totally wrong, their basic logic was right, because well before, at much larger distances than 10 to the minus 13 centimeters, around 10 to the minus 11 centimeters, is you see that the electron has a Compton wavelength. And there's a whole picture of electrons and positrons popping in and out of the vacuum, and all of that stuff makes the electron, from the classical point of view, effectively highly composite at a length scale of around 10 to the minus 11 centimeters. So, which was 100 times bigger, in fact 137 times bigger than the classical radius of the electron. So we've seen this over and over again, that the physics responsible for masses of, the physics responsible for the particle masses is revealed at the scale associated with mass itself. If that's not the case, if it looks point-like, and there's a huge gap of energy up to somewhere else, then that means that there's some physics totally decoupled, you know, from like 10 orders of magnitude far away, that seems to care a lot about producing this particular much more macroscopic scale. That's some kind of correlation, seeming correlation between very, very high energies, very short distances, and long distances of the sort that we've never seen before in any direct way in physics. Now, it's true that we seem to have indication for a similar correlation with the cosmological constant. And the similar logic that would have led you to expect that there should be some substructure associated with the Higgs might have led you to expect that there would be substructure at least associated with gravity at the length scale associated with the cosmological constant, that's around 1 millimeter. And there is no substructure associated with gravity at distances comparable to 1 millimeter. It's even been checked experimentally now. So that's an indication, these two problems of the cosmological constant and the Higgs that are naively tied to each other, even from this most naive back-of-the-envelope estimate calculation that I told you, are technically more tied to each other, might be tied to each other. They might both be telling us something, but there's something new happening here that we haven't seen before. Now, our astronomer friends have no difficulty saying the vacuum energy, the dark energy is super confusing, the theorists didn't expect it, we should go study it. Great argument. I fully support them. Okay? The analog of that argument in particle physics is the Higgs is super confusing. It's the same argument. It's the same problem. The Higgs is super confusing. We should go measure it. Okay? And I'll say sorry. Sorry?
There were these debates.
Indeed. And I would say, and it's just a fact that the analog of this experimental program associated with the Higgs is much richer than it is in cosmology, simply because it's not just one number, right? In cosmology, maybe a couple of numbers to see what the acceleration rate looks like, or the derivative of the acceleration. You can do a few things. Here, it's a very rich and detailed experimental program to measure, 15, 20 different ways that the Higgs can decay, can be produced, and so on. So it's a much richer experimental program, but it's the same basic question, and so that's what's at stake. Veronica.
So, what do you think is the most exciting or deepest consequence of the self-interactions of Higgs?
Well, I mean, I think the maybe I can. Can I switch back to some of the slides? I have some slides for some of these things. So just to say, well, let me skip past these things. Yeah. So let me. So this is the. I think this is most closely related to your question. So here's a very natural question. We wondered for decades, how is electroweak symmetry broken, right? And then using the Mexican hat picture that I hate so much, still, we learned for a long time we thought the Higgs was nailed to the bottom of the potential, and now we've made the first little excitations of the Higgs around the bottom, right? So But you might want to know, well, what does it actually look like? So that's equivalent to the question, how is electroweak symmetry restored as you go to higher and higher energies? Okay, so there's a natural continuation of the discovery. You see how it's broken. You want to know how is it restored as you go to higher energies. And so you could say, does the potential look like that, like we have in the standard model? Does it have more than one dip? Is it something much more complicated, effectively higher dimensional, more particles involved with it, and so on? Okay, now, so it's a question, what is the shape of the potential, is one way of framing the question. Now you might say, this is just a make-work project. You're pretending this is fun and important. It's so stupid. Obviously, it's the simplest thing, right? Why would you think it's anything other than just a Taylor expansion around the bottom like we teach in field theory books? Why are you pretending this is such a deep mystery? The other stuff is so unlikely and weird anyway. Why would you even think that it's worth checking? Okay? Now I want to point out, why do we think this is the obvious logic? It's the same dimensional analysis that we inherited from the picture of the world as a metal from our friends in condensed matter physics, from Landau and Ginzburg, right? It's just that dimensional arguments that tell us, well, whatever's going on, we have some effective theory at long distances, we write everything down compatible with dimensional analysis. That's why we think that's the shape of the potential, and that's literally the same logic that leads us to believe there was a hierarchy problem to begin with. Okay? So this is not some innocuous assumption that, well, duh, it's going to be dimensional analysis, you just write it down. That duh is exactly what leads you to believe there's a hierarchy problem to begin with, right? So even before knowing whether there was such a problem or not, you need to check whether this was true to begin with, okay? And could it be something else? Well, sure. It could be a quartic balancing against a sextic. It could be, that's a little dumb. This is slightly more interesting. It might not have a polynomial dependence at all. It could be like a la Coleman and Weinberg, for example. Okay? It could have a quartic. Now, all of these things, we have no idea. From the LHC, we'll have no idea if it's this or that or that. Okay? How are they different from each other? They're different from each other because in this example, the detailed shape of the potential is different, and in particular, the self-interactions are different. So the self-interactions here are 5/7 the self-interactions in the standard model. I have no idea from the LHC. Okay? So the first thing we'll discover by measuring the triple Higgs coupling, if it's different than the standard model, okay, great, then we know it's different. But if it's the same, then we'll have begun to even confirm that the dimensional analysis picture that was actually correct, okay, before moving on. That's thing A. But beyond that, there's something a little bit more detailed, which I think is very, very interesting. You might want to know how is electroweak symmetry restored in the early universe as we go to higher and higher temperatures. Now, in the standard model itself, it's not really a second order phase, it's a crossover, but anyway, let's loosely call it a second order phase transition. You might want to know, was it first order, right? Just experimentally. Now, we can't experimentally reproduce the conditions of the early universe in the lab. But there's a really interesting thing here to me, which is, in order for the phase, and as probably many of you know, there's even some motivation to have a strong first order phase transition. If there was a strong first order phase transition associated with electroweak symmetry breaking and some new source of CP violation, we could have a very nice theory for the origin of the matter-antimatter asymmetry. That's just an extra fact. But this is just a sort of bare experimental question. Can we say anything about how electroweak symmetry was restored in the early universe? Now, if you are going to modify the physics associated with the electroweak symmetry in such a way that the phase transition was first order, then that means two things. One, the new particles that are added cannot be too heavy, right? They have to be around, around the electroweak scale. Otherwise, it won't be important for the physics of the electroweak transition. Two, they can't be too weakly coupled to the Higgs for the same reason. They have to do something and change the nature of the transition somehow. So now it becomes a very interesting detailed question. Let's say in a wide class of models that allow the phase transition to be more strongly first order, you can ask, in those theories, how big is so you'd expect deviations in the couplings of the Higgs, and you'd expect to be able to produce the new particles at the higher energy collider. So it's a concrete question. you take any model you like that makes a phase transition first order. In that model, how big is the correction to Higgs couplings you would see, and are the new particles accessible to the next collider? And that gives some invariant measure for how much more precision you need and how much more energy you need. Okay? And the happy answer is that the factor of 10, 20, 30 on the precision for the Higgs coupling and the factor of 10 for the energy are enough to cover, and people have stood on their heads to build complicated theories to make it as hard as possible to see. And even then, you can basically cover it. But you take the simplest possible ways that can happen. Let me just give you an example. The simplest thing that you could do is to get a first order phase transition is to have, you might imagine that there are new sextic interactions between the Higgs, and associated with it, any physics that generates this can also generate some other short distance interactions. And you might imagine getting these things from the Higgs interacting, for example, in a very simple way at tree level with new scalar particles, these things that are sitting there in black. Now, you take one of these simple theories, like this one. Okay? The Higgs just couples to some new spin 0 particle in there, and that gives us both these corrections to the Higgs self-interactions to drive the first order phase transition, as well as this thing that modifies the couplings of the Higgs to the Z. And you find a very clear, very clear correlation that there's a correction of the coupling of the Z to the Higgs that's got to be bigger than about 3%, and the mass of the scalar particle has got to be lighter than about 2 TeV at absolute biggest, okay, in order for the phase transition to be first order. Now, the Higgs factor, we will measure this to 0.3% accuracy. So a factor of 10 better than that. And up to just about 1.5 TeV, no problem for seeing this guy. And that's without thinking too much harder about it to cover the whole range. So there's a concrete thing. When I said there are questions where this degree of energy and this degree of precision will give you an answer to something, I think we will know. If we see the if we see a deviation, that's one thing. If we don't see a deviation, we'll also know. We'll know the Higgs looks point-like to itself. We'll know with pretty high confidence the nature of the phase transition in the universe as we go to higher energies was probably not first order. Okay?
Do we know from astronomical observation that the matter-antimatter asymmetry is correlated with this phase transition? No, we don't. No, and even if you just see this, it's not enough to tell you that they're correlated. You also need a new source of CP violation. But of the many ways that people have thought about over the years to explain the matter-antimatter asymmetry, making use of such a phase transition is an interesting. I should add that something kind of exciting, but it's at the borderline of working. Is that phase transitions at around these energy scales also lead to gravity wave signals that could be seen at LISA. Okay? In detail, it's not 100% overlap between the ranges of the parameter space. So, but there is some overlap, and so that's also interesting.
Question? Yes.
It's a very speculative question, but even though it's such a long way in the future, do you have any instincts or insights into how stuff like the Higgs and so forth might be used in sort of engineering and technology?
Yeah, I think it's very, very unlikely that anything to do with the Higgs will have anything to do with anything practical to do with technology. And I want to be very clear about this because I think in particle physics we give sometimes glib answers to these questions when there are much better answers that we could give that are more concrete and actually more convincing. But there is a kind of glib answer which I believe, I mean, on a long enough time scale I believe. The glib answer is, for centuries, things that we've done by curiosity-driven research, 50 years later, turn out to revolutionize the world. Truth, okay? Definitely true. It's definitely true that Michael Faraday told that MP that who asked what radio waves were good for, I don't know, sir, but one day you will tax it. Okay, that is a true thing, and it happened. It's true that only 20 people in the world cared about quantum mechanics when they were discovering it, and it is responsible for 2/3 of the world's GDP. This is all true. However, it's also fair to say that all those things did not involve, taking 10% the power of the city of Geneva to run a machine to produce a million little particles that live for 10 to the minus 24 seconds, right? So I think the honest answer to the question, can I imagine the Higgs itself will be technologically useful? Absolutely not. I would be astonished if it's technologically useful for anything, okay? In fact, yeah, I would bet a very large amount of money it's utterly useless, okay? However, there are much better answers to why we should be doing this. Not just merely, general inspiration, which is a big deal, by the way. There's not just the general inspiration for belonging to a group of humans that are doing incredibly hard and difficult things that take decades to accomplish. The problems of the world are problems that increasingly are going to take the efforts of many, many people decades to confront. And having a small group of people who have been good at doing this for centuries is a good thing, just as a template for how to go about doing it. Of course, when you try to struggle to solve very hard technical problems, there are all kinds of other ancillary things that come out of it. We always talk about how the World Wide Web was invented at CERN because it helped by the necessities of particle physics. But an even more hard-nosed level than that, there was a nice study that was done. I forget who it was commissioned by, but it was done to talk about the economic return of Fermilab. Okay, and it's really hysterical. I didn't know some of these numbers, but some U.S. Census Department actually puts a dollar figure to having a PhD. Okay, so a PhD is $1 million plus $1 million. Okay, as far as the country's economy is concerned. I don't know how they come up with this number. Whether it's something to do with the amount of tax revenue. I don't know how they get it, but that's that. So just by that measure alone, the number of PhDs produced by Fermilab equaled the cost of the machine. Okay, so now I'm serious. Okay, now on top of that, there are all sorts of other detailed things that they helped in developing cloud computing. Okay, now you can't say if Fermilab didn't exist, cloud computing would not have come along, but they certainly accelerated it. Let's say you just say it was accelerated by 6 months, a year. Okay, then the amount of net addition to the economy just by that 6 months or a year is another few $billion dollars, given the scale of the project. Never mind magnets for MRI machines around that. Just development of those things actively involve the participation of Fermilab theorists, of Fermilab experimentalists. So all told, the economic return of Fermilab, and this was not something commissioned by the particle physicists, it was something that was done by other people, was several times the cost of the machine. So there are broad inspirational things which I think are incredibly important. I really think that thing I said about feeling you belong to a people that just take it as something they do to attack almost impossible problems and at least devote some fraction of their efforts to trying to solve them. That's kind of a big deal to feel that you belong to a people who are like that. And if you stop believing that you can do that, it has lots of interesting, bad, I think, trickle-down effects elsewhere. But there are much more concrete things of the sort that I talked about. Could we guarantee they'll keep going on? No. That's the honest answer. Is there a track record of this happening for a really long time? Yes. And so I think that's the most honest answer I can give. I do want to highlight a couple of things, though, towards the end here. As you see, there's a lot of stuff we could have talked about. But, oh, sorry, just to show the favorite thing of the particle physicists is a picture of the maps of the world with giant rings on them, okay? So this is what our friends at CERN are thinking about for these circular machines. There's, I think, an 80-kilometer tunnel. It goes underneath Lake Geneva. It's not going to make the Swiss people very happy. But anyway, there's the LHC there. And our friends in China are also doing the same thing. They actually now, when they first started, they had one site pretty much that they liked a lot around 300 kilometers northeast of Beijing. There's a 50-kilometer tunnel and a 100-kilometer tunnel.
And nowadays, they're not even drawing the 50-kilometer ring anymore. So it's just a 100-kilometer tunnel. And there's many other sites that they're talking about around the country. And in most of these places, the local government is very excited about supporting it. But what I wanted to point out, this was the issue that's come up a number of times already, the 10 billion in your favorite units question. So these machines are very expensive, but as I mentioned, this is a slide I got from Yifang Wang, who's the experimentalist in China who's leading this effort. The BEPC is a little circular electron, low-energy electron-positron collider in Beijing that got China into particle physics in 1984. And back then, it cost 10 to the minus 4 1984 Chinese GDP. Okay? The superconducting supercollider was around 10 to the minus 4 American GDP. LEP, 2 10 to the minus 4. The LHC, 3 10 to the minus 4. The linear collider in Japan, 2 10 to the minus 4. The cost of the circular electron-positron collider, that's a CEPC in China, and the super proton-proton collider, that's what they call their 100 TeV collider there. Okay, their numbers are comparable. They have a very detailed cost estimate for the Higgs factory. This is an easy, on the scale of things, a machine that you can build. You have to build a 100-kilometer tunnel, and they're not sugarcoating it. It's $5 billion. Whoomp. Okay, but that's it. There's it's not. It's that there's no hidden, scary extra costs associated with it, as far as anyone can tell. So really, there's no obstruction of any sort, I think, to actually doing that. My own feeling is that if there was a mechanism for active international collaboration and cooperation on this machine between the West and China, that would actually happen. And I'm very surprised because all the difficulties with this project are completely backwards to what I would have naively anticipated when I first started following it around 3 years ago. The most naive thing is it's so expensive, they've never done anything like it before, they'll be scared to try, and so on. Okay, there was some of that in the beginning, but I think the scientific case has been made very clearly. Everything is, I think, pretty clearly understood. The cost is not an issue. They're looking to do some big thing. I thought the easy part would be the international cooperation part. That's the part which is almost impossible right now, especially with the US. Okay? And I could tell you insane stories about this relationship at the moment. It's really bad. It's it's going south. Okay? It's going in exactly the wrong direction. But I think if there was a mechanism, and I think it would be geopolitically great to at least have some large project where there was friendship between East and West rather than growing tension and animosity. So having 10,000 people going back and forth would be, I think, a good thing. Then, huh?
Think of Russia back in the day. Something similar. You have the science connection with Russia.
Well, I mean, CERN was very helpful. I mean, exactly, yeah. So, well, but I think that this would have a rather different role. But I agree. Like having something, being involved jointly in a large-scale, ambitious project for humanity would be a wonderful thing. And I think if a mechanism, I mean, I'm talking about a kind of a bureaucratic scientific mechanism was set up to make that possible, then I think it would, that's my guess, my feelings, that it would probably just happen. But that's the part that I thought would be easy, which is hard. And all the stuff that I thought would be hard turns out not to at least be a showstopper. So, but what I want to say is the E plus E minus collider, there's no difficulty with going ahead with it. The proton-proton collider, things are driven by, you want to make the cost as low as possible. The cost of proton-proton colliders is driven almost entirely, a large part, by the magnets. Okay? And what you need if you want to get a 100 TeV collider in a 100-kilometer tunnel is you need to have 15 Tesla magnets, 16 Tesla magnets. As a calibration, the LHC has 8 Tesla magnets right now. Okay? So you need to get magnets that are twice as strong. Now the people who know how to make these magnets, mostly at Fermilab, they're maybe up to around 11 and a half, 12 Tesla. They think that they can get to 15, 16 Tesla on the 10, 15-year time scale. Okay? And then there's a question whether they can get there, whether the costs are scalable, and so on. So you don't want to pull the trigger until you know what you're doing with the magnets. To give you the world's worst way of talking about the cost of accelerators, which I'll only do because I assume we're mostly friends here. This is a way never to describe it to the general public, is that a collider costs about as much as having Ferraris parked end to end around the ring. Okay? Okay, so that's why it matters a lot, really a lot, to make sure that you've got the component parts per unit length worked out to be as cheap as possible. Now, a really great thing, I borrowed these two slides. Yifang Wang was just at the Princeton giving a talk about the latest things going on with this project, and he talked about two things that I thought were very exciting that I just wanted to share. Both having to do with cost issues, and they're both speculative, but it shows the kind of thinking that's going on. One of them I think is really cool, actually has to do with one component of not the proton-proton collider, but the E plus E minus machine. And here they have a very interesting idea. You want to, so one of the components of any accelerator is the kind of early system where you first, accelerate particles a little bit to put them into something that's called a booster that sort of takes them around, puts them in a ring, and then boosts them to the highest energies before they actually collide with each other. And here, if you have a 100-kilometer around tunnel, if you do it in the conventional way that people have talked about, where people have used relatively low energies going in. So you accelerate the E plus E minus to around 10 GeV going in. Then because they have to go around on this 100-kilometer thing, the magnetic fields required is so small that the Earth's magnetic field starts messing with it. Okay? And so that's bad. It's much harder to control. It's a kind of significant part of at least the cost of this system to deal with it. So they had a great idea, I think, which is to use this fancy technique people have been talking about for years, using plasma wake field accelerators to get huge energy. Okay? People have been talking about the ability to get LHC energies in a football field using gigantic lasers to give you the huge electric fields that you need to accelerate electrons. The problem with this idea as the mechanism for the collider itself is that it's a very messy way of accelerating particles. So you take a few electrons and you smash them and they spray out in all sorts of directions, and it's hard to collimate them enough to get the luminosity you need to get enough collisions for things to be interesting. But here, the plan is to do something, they're still working on it, but the plan is to do something really cool, which is use a plasma wake field accelerator to actually boost you to around 45 GeV, but into the booster, into the ring, which then takes care of collimating. They just go around and around and around and takes care of collimating them anyway, and then the booster takes them from 45 to the higher energies they're at. So this solves the problem with their tiny magnetic field, because they're going in with much larger energies to begin with. And if it works, it would be an interesting cost-saving device on at least this part of the system. And I think even more interestingly, it would be the first example of this plasma wake field stuff being used for something real, right? It to be actually used in an interesting, important way as a component of an accelerator. That's one thing I thought was cool. Another thing which I think is really cool is that there's something that people have been talking about in condensed matter physics. It's sort of been a hot topic, as far as I understand. It seems really interesting for a number of years, which is iron-based high temperature superconductors. And this is something which has been being, normal high TC superconductors there are these sort of, as I understand, more difficult to work with ceramic materials and so on. They'd like to use iron cables instead. And their particular application for colliders is a really perfect one for this, because they're not obsessed with getting to super high TC. They're running this experiment at 4.5 Kelvin anyway, so they don't need to get incredibly high TC. They want to get at 4.5 Kelvin something which is carrying enough current to make it worth it. And so this is really interesting that this is involving these guys talking with a lot of material scientists, people working in this field, and it's not obvious where it'll go. But if they're optimistic about things working out, they could get much higher, much stronger magnets than even 15, 16 TeV. They're 15, 16 Tesla. They're potentially talking about getting 20, 24 Tesla magnets at a much lower cost if they actually manage to get the material science working. So let's say that works. Very optimistically, if it works, then the cost would be much lower. They'll be talking about, like $10 billion for the proton-proton machine at 150 TeV. Okay? Because with 24 Tesla magnets in there, you can go to much, much higher energies. Now, this is very optimistic. It might not work out, but this is 30 years from now, right? Whenever we're thinking about these things, it's, I'm going to be dead, but we have to have some optimism also that things develop, technology develops. You're not going to just build this machine in 30 years based on things that we knew how to do 20 years ago. But having said all of that, let me say that you should not have the impression this is some impossible, difficult to build 100 TeV, my God. We are talking about the SSC, which was half that energy, and we could have had it running in Waxahachie, Texas in 1999. The idea that we can't do something that we were trivially going to do in the year 2000, 40 years after that, right, is just absurd beyond comprehension. There's no technological difficulty. There's no economic difficulty on the scale of things that we've spent on this science before. I think it should just be done. But these are some examples that there'll probably be new ideas coming along as you start working on these things. Interesting opportunities for collaboration with other parts of physics, material science, all kinds of cool stuff. And you have to have your mind open and alive to the possibility that these things are conceivable, and then good things can start happening.
So I agree with you that the fact that politically we can't talk about this percent of GDP approach is some weird disease that hopefully we'll get over. But I want to just escalate that a little bit and say, when I get a pay raise, I don't buy proportionally more toilet paper, right? I spend it on new things.
Sure.
And so, in fact, we should be asking, what do we want to spend an increasing fraction of the GDP on?
I completely agree with you. Yes, I totally agree with you. Right.
Conversation in that direction, whether it's education or research or Broadway musicals, whatever it is, we get to spend an increasing fraction of GDP on cool stuff.
I totally agree. And by the way, I should really say again, I don't think it's axiomatic that we have to keep doing this because we have been doing it before at all. Okay, and I actually think had the science turned out differently, again, I have a heterodox attitude about this, but had the science turned out differently, had we discovered, like what people imagine, 300 GeV gluinos at the LHC pouring out, and then you'd build a linear collider, do precision measurements, then I would say. We could keep going to 100 TeV if we want to see what's there. Great. But if that's not a good enough motivation, then I wouldn't see the same intellectual level of motivation for going further as we do now. That's the irony, right? Like seeing less means we need it more because the scale of theoretical confusion is vastly larger. Right.
But then, in due course, someone will just build it in their garage.
Yeah, well, and I think, but I think here there's a serious conversation to be had. I'm not, again, I don't think the answer is axiomatic ahead of time, but I do remind you that when the SSC was canceled, part of the argument from people outside particle physics was, oh, just wait a few years and those high TC superconductors will make everything super duper cheap. 40 years later, we're still waiting for one iota of that promise to come true, right? So you can't. Well, you have to decide because this is the sort of thing that if it stops, it's not trivial to restart. Okay, so the degree of expertise that's needed, the thousands of people, already it's getting dicey because there are not droves of people in their 30s who know how to build these things. The people who know actually how to build these things are significantly older than that. And unless they start doing it again and teaching other people actively how to do it, it's not like if we stop doing it 40 years later, say now we're going to start doing it again. Okay, now so we should decide. Therefore, we should decide: is this a moment in human history when we're going to stop this path? Okay, and I should say that whether we want to or not, there are physical limitations. No one is going to build a 2,000 TeV collider in the way that we're doing for proton-proton machines on planet Earth for just physical reasons. Okay, so it's not like there's 5 next steps to go. This is probably the last, if not the penultimate step. I should mention there's a wonderful crazy proposal by Peter McIntyre at Texas A&M for what he calls collider under the sea. That would be a 500 TeV collider underwater around the Gulf of Mexico. So that's a way to get to around 1,000 kilometers without building tunnels. And he has crazy, cool ideas for using thrusters that the Navy has constructed for other reasons to control this buoyant contraption 1,000 kilometers around. So anyway, if you want to eventually go to the 1,000 kilometer scale, we're not going to do it by digging tunnels. You could go under the ocean. And so we could get to 500 TeV, maybe, but there are just physical limitations, so we're not going to go much further than that. So if we're going to stop doing it, then it's a major decision. We're stopping doing it, and we're stopping doing it now, at this moment in history. We can't just say, oh, let's stop it now, and we'll come back and do it again in 40 years. It's not like that. But I'm not saying there's an obvious answer to this question. But I do think that we should make the most honest case we can, and I think it's a good one. I think it is a good one.
Yes. Well, I just want to throw in this anomaly, and that is you're talking about the international situation and the tensions. After all, CERN is designed to overcome peace.
Absolutely. That's right.
And so it's so important to continue this.
I totally agree. Yeah.
People begin to turn on China, and we have people, our graduates, that are working there. Do I go there? Do I dare go there? Yes. Gotta keep it up.
Yeah, well, I mean, that's why I said I think that's a major selling point from my point of view for this project is as a potential for not just international but particularly U.S.-China partnership. I think if there was yeah, I think it has potential. It has really good potential along the lines of what you said for CERN, probably even more so. But as I said, if I'm pessimistic about anything right now, this is what I'm most pessimistic about because I don't see any mechanisms, and in fact, just obstacle after obstacle, bureaucratic obstacle after obstacle, scientific bureaucratic obstacle after obstacle put up against the possibility for Americans to participate in a project like this right now. But that might be a local phenomenon. It's not. I have no idea how to continue that into the future. And it's not important that this problem is solved on the 1 or 2 year time scale, but it's important that it's solved on the 5-year time scale. I forgot to say they're kind of at least in China their plans are to they're already they're completing a conceptual design report for the Higgs factory, and they would like to ask to go for it. I mean, ideally they'd like to start construction in 2021, 2022 for the 100-kilometer tunnel, and have Higgs factory collisions by late 2020s. So that's what they're talking about. So I think if in the next 5 years it still looks like a complete mess as far as the possibility for international collaboration, that'll probably hurt significantly.